Okay, we'll start with Chapter 3, problem number 44. And like the others, we want to draw a timeline. But with these growing annuities, it's a little more difficult to draw a real precise timeline. It says here that we're going to have a payment come next year of $1,000, and that payment's going to grow every year for 20 years. And that's why it's more difficult to actually draw the timeline, because this is going to be in year 2. It's going to be $1,050 because it's growing at 5% a year. I'm going to calculate all of those out, but the idea is the same. I want to find the value today, so that's the present value. The formula, the value today, or the present value, is going to be equal to the payment, which is 1,000, divided by R minus G. And you can see this in the text. You can see that formula, and here R is going to be the discount rate of 10% minus G is that growth rate of 5%. And this will be multiplied by 1 minus 1 plus G raised to the n, which is 20, over 1 plus R raised to the n, which again is 20. That's going to be equal to $12,112.08. Now, just a couple of observations. This portion right here is going to be the value of an annuity that grows forever. So this is similar to the perpetuity, which would be 1,000 divided by the interest rate of 10%. But if it grows, then we subtract that growth rate in the denominator. So that's if it goes forever. This takes care of the portion that says, look, this is just 20 years. Okay, so let's look at number 45. And 45 is going to be a little more difficult because we're combining growing annuities in different ways. So I'm going to draw a nice long timeline here. Today it says is your 35th birthday. And you want to retire when you're 65. And you're going to make deposits into that account, and those deposits are going to grow, and those deposits are going to grow, I'm going to put here, they're going to grow at 3%. You want to make withdrawals beginning on your 71st birthday of $125,000. I'm going to leave the thousands off, and you want those to increase because you know that there's going to be inflation and you need to have more money to live comfortably. Those are going to increase at 2% per year. You want to find out what these deposits are going to be. Okay, here's how I can think about that. I know the formula for future value of a growing annuity. The value at year 65 is going to be equal to the payment times 1 plus R to the n minus 1 plus G to the n all over R minus G. Now, what do I have? I'm trying to solve for payment. I know R, my discount rate in this case, so I'm going to write it here. R is equal to 7%. And I know the G in this case, this is a 3%. I don't know the value in year 65. So in order to save money, I need to know my target. How can I get that? What I can do is 2 steps. Find the present value of these payments. The present value is going to be the value in year 70, and then take that back to year 65. So I'm going to do that in red. So the value at year 70, now I need the present value formula for a growing annuity, is 125,000 divided by the discount rate of 7% minus the growth rate of 2%, because these are growing at 2% while that was growing at 3. So make sure you get your growth rates straight, times 1 minus 1.02 to the 21st, right? Because this is going to be 21. It's 1, 2, up to 21 total payments. That's divided by 1.07 to the 21st. So this is equal to 1,584,866.86. Within the value at year 65, back to chapter 2, is the value at year 70, 1,584,866.86 divided by 1.07 to the 5th, so that's equal to 1,130,738.17. That becomes this number right here. So what I have now is 1,130,738.17 equals payment. That's what I'm solving for, times 1 plus r is 1.07 to the what power? How many of these do I have? I have 41. Right? I'm making 41 deposits because the first deposit is made today. The last deposit is made at year 65, minus 1.03 because it's growing at 3%. I'm increasing the deposits each year by 3% to the 41st. All that divided by 0.07 minus 0.03. Now you just do the high school algebra. You find that payment to be $8,012.27. Okay, so let's go on to question number 46. 46, you're going to have a timeline again, of course, and you have a choice. Today you can receive $300,000, or you can receive payments that occur the following way. There are 25 of them. The first one is made at year 5, and then year 6, and that's going to be $10,000, but they grow at 10%. So they're going to go here, they're growing at 10%. So there are 25 total payments. So this goes to year 29. And the question is, would you rather have these payments or the $300,000 today? So I need the present value of all this. Using the present value formula, I'll find the value in year 4. So step 1, the value in year 4 is equal to, when we go back to that old formula, the payment, $10,000, divided by the discount rate, which the discount rate is our required rate of return, 6%, minus the 10% growth rate. You're saying, wait a second, that's going to make it negative. That's fine. I did it this way to show you the formula still works, because watch what happens. 1 minus, this will be 1.10 because it's 1 plus the growth rate, to the 25th power divided by 1 plus r, which is discount rate, 1.06, and that as well is going to be to the 25th power because we get 25 total payments. So the value in year 4 is equal to $381,117.91. In other words, at this point, year 4, right here, I don't care if you give me 381, or if I receive these payments of $10,000 per year that increase, at 10%. Step 2, the value today is equal to the value at year 4, 381,117.91. This is back to chapter 2, divided by 1 plus the interest rate, 1.06, raised to the 4th power because I'm going back 1, 2, 3, 4, and that's going to be equal to 301,881.08. So given that I have a discount rate of 6%, I would prefer to have the annuity because it's worth more rather than the 300,000. So I pick this growing annuity. Okay, let's see if we can get question number 47 in. So, question number 47. Again, we're going to draw a nice timeline. It says you're willing to pay $8,000 today. So here we are today. You're willing to pay $8,000 for a money machine that generates the following cash flows: $1,000 per year for 5 years, with the first payment made next year, up to year 5. 1,000, and then beginning in year 6, you're going to get an unknown payment. I'll just put P, and that's going to go forever. What does that unknown payment have to be if the discount rate is 6%? So we're paying essentially for two cash flows. This cash flow, let me do it this way, paying for two cash flows. The cash flow here I have in red, and the other cash flow, the one I have in this pinkish purple. Okay, so what's the value of the cash flow in red? N is equal to 5. Payment is equal to 1,000. Interest rate is equal to 6%. Future value is equal to 0 because there's no additional payment in year 0. Plug that in, press the present value key. That in fact is the value at time 0, and that number should be equal to $4,212.36. So if you're willing to pay $4,212.36 for the $1,000 cash flows, then look at the other set. That means for these, you're willing to pay how much? $3,787.64 to get the cash flow that starts in year 6, year 7, year 8. It goes forever. I just don't know what that payment is. Okay, so does that make sense? We're buying two chunks of cash flows for $8,000. The first one's worth $4,200, so the next one's worth $3,700. I know the formula. I'll put it right here, the value of a perpetuity. So let me write it this way real quick. The present value of a perpetuity is equal to the cash flow over R. Present value means one period before the payments start. Our payments start in year 6, so the value in year 5 is equal to the cash flow, that's what we're looking for, over R, which is 6%. So if I knew the value in year 5, I could solve this. Well, I know the value in year 0, I can find the value in year 5. So the value in year 5 is equal to the value in year 0, 3787.64 times 1.06 to the 5th, which is equal to 5,068.71. So substituting that one right there, we can find the cash flow is equal to $304.12. Okay, so just a quick review of this. I'm willing to pay $8,000 to get both sets of cash flows. I can find the value of the first set of cash flows is roughly $4,200, which means the value of the other set of cash flows is $3,700. That's the value today. Okay, but those cash flows start in year 6, they go forever. I know this is a formula for a perpetuity. So if they start in year 6, because present value means the value one period before the payments start, that means the value in year 5 is equal to the cash flows that begin in year 6, like they do in my problem, divided by the interest rate. So if I know the cash flow in year 5, this is just an algebra problem. Well, I know the value today. If I'm willing to pay $3,700 today to get cash that starts in year 6, I'm willing to pay $5,000 in year 5 because it's chapter 2 problem, present value times 1 plus R to the T. So that's it for 47.